Start again with the second lecture of Drª Cristina Chiappini. So Cristina, please.
Obrigado. Bom, if somebody was not here in the first lecture, the idea was to first discuss actually I changed a little bit. We discussed last time some basic concepts of how to use the information on the galaxy to then get many insights about several topics. I finish by saying there were three revolutionary things that had happened in the last 10 years, and we discussed the first one, which was asteroseismology, right? That we could get mass and radius for stars that are very far away. So we'll continue a bit of the first, and then we dive into the second. That's where we're going to use this information together, what we call we'll use these three: information spectroscopy, astrometry, and seismology, to investigate some questions about the Milky Way, especially on the disk today. And then we are going to dive in the third lecture into the bulge, because that's where we have very new data as well. And the bulge takes almost two pieces, because then we go to what's going to happen in the future, and there's a lot in the future happening in the direction to have a more precise and general view about the inner parts of our galaxy. And that connects with the amazing results we are seeing from JWST at high redshift above 5, where you are seeing bulges information of big galaxies for now, but maybe our galaxy has a bulge from the very pristine epoch. So these were like the 4 lectures. So let's go to the continuation of what we discussed. So I had finished with this transparency, that there has been 3 observational breakthroughs since 2010, and they have brought to us the difficulties that we had discussed. So we are overcoming these difficulties. One is volume coverage of the Milky Way, the obtention of a lot of 6D phase space. We discussed these positions, velocities from Gaia. We can do that, so we can also analyze orbits, and the ages and distance precise. Ages is still the problem, right? And we discuss, among these 3, we discuss the first one. So today let me briefly introduce the second and third, and then we go further. So the second revolution is Gaia. And Gaia is amazing, has impact in several areas, but was made for, if I may say, mapping the Milky Way. So that's the main objective of Gaia. But needs to be combined with complementary information so that you can do this. Because you can get the parallax from Gaia, and if you invert the parallax, you have the distance, but this is valid only at a very nearby volume, where the uncertainties in the parallax are minor. As when the things come to a little bit larger uncertainties, diverge, and the 1 over pi cannot give you the information on distance, and you need complementary information. You need to have a Bayesian approach, combining also Gaia photometry, and to also overcome the extinction. So it doesn't work when you are in an high extinction region, but that's where we want to go. So Gaia came, Gaia is the son of Hipparchus in the 90s, that Hipparchus observed around 118,000 stars. This is a transparency from this guy. You see here, that's Hobbes. He is now the PI of our proposal for a new Gaia, that I told you about, Gaia in the infrared, so the next Gaia. So here he's defending the project in front of the ESA committee, and he put this transparency, which I like. So everything started from Hipparchus in '89, and there you had the first time this sort of precision 1 to 2 mass per year of accuracy for this parallax, and in proper motions, but very in a volume very restricted nearby. And Gaia extend this is 100 times more accurate. We have micro arc second precision, and as we said before last time, 1.7 billion objects across the galaxy. So really is like another scale. And here the Gaia has having the data release, and each data release was almost like a party. We organize a party essentially in the institute, because especially data release 2, that means from that day on we are working in a completely different way, because we don't have anymore a bunch of points, as we had. I also said last time, we have millions of objects in your plots. And the way you're gonna work with big data is changing. So you're not going to do this in your laptop. If you want to work, I mean, you can do several projects, of course, with specific data sets from Gaia, but we were interested in using the full data set of Gaia to construct these maps of the Milky Way. And so here is Anthony Brown and Timo Prusti, who was the project science, and he's the DPAC person responsible for Gaia. And there has been the large data release was in 2018, and then in late 2020 was the extended the EDR3, and now in the third data release of last year in June, this came also with some radial velocity. So Gaia, apart from giving you proper motions, parallax, color, give you also radial velocity for some objects. And these are for bright stars, and so there is a big effort from the community to complement the Gaia data with more radial velocity and more chemistry. And that's what we're going to do with instruments such that you probably heard about. Foremost telescope, that is a multi-object spectrograph with more than 2,000 fibers that's being installed in Vista telescope, and in the south, and the WIV, which is installed at ESC in the north. So the idea is instruments with thousands of fibers to follow up, to complement the radial velocity that Gaia is giving in this data release. And then going fainter, of course, and extending the map, right? So to give you an idea, the Gaia is called early data release 3, because the data release 3 is where we got the PRP spectra, is more information, and the radial velocity for some stars. But the huge thing that we had already in the end of 2020 was also an improvement in a little bit improvement in parallax with respect to 2018 data, and also important improvement in proper motion. So that was important for us in this work I'm going to show you. So you have stellar positions, brightness, and you have a color for stars, and you have also a lot of extragalactic source, and it's amazing. It's an amazing data set. And all this, you have the web page of Gaia, you have all the information, and you can play with the data, and they help you. If you have a question, you can send, and it's really fast that they answer you, so it's really nice. So we wanted to not to get the easy hanging fruits, as we say. We went straight to dive to the difficult project, which was to treat the whole data set and to immediately complement the Gaia data with more photometric bands, so that we could go to high extinction and extend this volume. So we then combine the Gaia data with APAS, 2MASS, all the photometric information. And if we had spectroscopy, we use that as well. And then you compare, we construct this spectrophotometric model, where we compare with stellar models, and then you can extract using galactic priors, and then you can extract parameters that we are interested, of course, primarily distance and extinction. But you have secondary products that could be, depending on the quality of the data and where you are, isochrone ages, masses, and the temperature, and log G if you don't have things. So this code is called Star Horse. It started from a collaboration I had with a person in Brazil, which is Basilio Santiago from Porto Alegre, and then was developed a lot by my two PhD students, Friedrich Anders and Anna Queiroz, that has been working on this with me in Potsdam. The beginning was very tough. This is the first time we could combine, so we were really the first group that combined Gaia data with all this information, and could produce already in 2019. So it was a steep learning curve because we are not part of Gaia officially. And then you have this kind of CMDs corrected by extinction, and you have like there up to magnitude 16. You have, I'm showing you a CMD of 16 million objects. Here, a CMD with some problems here of quality flags that we treat and discuss in this very huge paper. But here you have a CMD with 265 million objects in the galaxy. And then we want to now having the extinction and constructing the maps, we will map the galaxy. And that's what I'm going to focus now here to show you. So soon after the data release of Gaia, Bailey-Jones published their map of the galaxy, their distance, in 2018 still, because he's part of Gaia. And that's the, for example, X and Y view of the galaxy with the Gaia data, where in the center, where you have the largest concentration, is where the sun is. So you have a lot of data around us, and you see something in the direction of the galactic center here, right? And this is using only the Gaia data without combining with extra photometry, is using some geometric way to treat and to increase the volume in which you're not using 1/, parallax, but is using a different method, but without combining with external other data. And for the same, this has some problems, this approach, because it underestimated the distance to very luminous stars. It worked better for non-giant stars. And then, as soon as we had combined the data, that's what we saw. For the same data, when we run our data, so this, to give you an idea, at that time the Star Horse, we were learning, so that time the Star Horse was taking time to run spectrophotometric code Bayesian approach, using all the information we could, but it was clearly that we were seeing the galactic bar. And then we, of course, we were afraid that maybe it's our prior, but the prior was not in this direction, but we were the first group seeing that. And so this is what happens when you combine the Gaia data, the first DR2, which still had some problems, and you see the density, and you see you reach the center of the galaxy with the Gaia data with good distance, good extinction, and then you can start doing really a lot of things. So that was what the Gaia end of mission expects to cover as a volume. This is a simulation. The goal is the 3D map of the Milky Way. That's what is expected. And this is what we were already getting after less than 1 year after the data release. So it was a lot of work of the group, the young people of the group call it Star Horse. And after, in 2021, with the DR3, the group, the Gaia group made again this paper where they give distance for 1.47 billion stars, and they use our Star Horse to compare if their distance were good, and it was it was a very good comparison, because this here, the paper that is Queiroz 2020, is the one after the one I showed you before, is the one, so the one of Anders 2019, we just combined Gaia data and photometry. But then in the one of Anna Queiroz 2020, we combined Gaia data with photometry and spectroscopy. So use all the spectroscopic surveys in the galaxy, combine the input of spectroscopy to help the program to find the distance and the extinction. And so this became like a good data set for people to compare with, and that's why when the Gaia people run this, they compare to this distance. So now, I think the Zoom fell out. No? Okay, now I got a message. Okay, so then Corinne Bailey-Jones, using what they call photogeometry, which is exactly what we do, which is combine photometry and Gaia, he can already find here what we were finding too, the bar, right? And then he has a correction for his geometric approach and starts seeing the same. Meanwhile, so what happened now? Okay, so we, on the other hand, also made some improvements, and with this data release of Gaia from end 2020, the parallax were more precise by 20%. There were some problematic parallax in the first release of Gaia. They were identified by this very nice way to do it by Hibisky in 2021. So we have used this, and we also use a sky mapper that became public as another photometric band. And then you could combine all this data and make a better map, which is, and this is something Friedrich likes a lot. We improved a lot the how we go with the code. We go faster, so we decrease the footprint, CO2. He always say that, okay. So this data set, I have to say that all this happened during COVID, so with all the things happening. So a lot of what we did had to be online, so it was not so easy. And then finally, in 2021, we managed to meet in person again. So we had a beer because we are in Germany, and that was very nice. So here you have Friedrich Anders, Barbara Queiroz, Arman Kalatian, who is a colleague of mine, and Basilio was not there, of course. So this is the last maps we have, and what I have to say, the maps, so the distances, the extinctions, the secondary parameters like temperature, log G, this is all made public. So we have a database where you can download. We have a page where we explain how you use the data, how you download, how you query the data. And so here is just a distribution now, X and Y. So like if you're looking at our galaxy from above, you see the SMC, the LMC, the Sagittarius. Here now I made a close-up, and you see again the bar with less strange things happening. Here, if I see our galaxy from side, of course, Gaia does not give me anything that is very much into the plane when I go, because it cannot reach, because it's high extinction. And here's a zoom of that, right? So here you have a missing information. And so this is for around more than 300 million objects in this map. You have very good parameters, which is this good flags means. So this is very nice that you can use. This is an example of our web page where you can download the data, how you can use with DQL to use the data, and so on. So the paper says, and there's all 2021, but actually it came out as 22. Okay, so this is only photometry, but now we can do it with spectroscopy the same. So we now combine the data, photometry, EDR3, Gaia, and all spectroscopic surveys. And you have to understand that the moment that Gaia came, before Gaia came, there was a lot of spectroscopic surveys over the galaxy covering different volumes, right? So now I have different spectroscopic surveys of different qualities. Some are high resolution, some are low resolution, and so on, with some difficulties, and so on. Here we run Star Horse, using as input also the spectroscopic values like temperature, log G, but we didn't make an effort to try to homogenize this, so it's the input of each of the surveys pipelines. So if you have Gala suggests this is the parameters of these stars, you use these parameters as input of Star Horse to get the other information and get your distance. And so these surveys cover the whole galaxy, north and south. So you have Lamost, which is the low resolution, the medium resolution, the apogee, and so on. So this is what we do. We combine, and in this last paper, which is 2023, we get 11 million stars for which you have spectroscopic parameters plus photometry plus Gaia. Okay, and this is also what we're going to use for maps. And this is photometry use. So as I said, the main parameters are the distance and extinction, because without extinction you do not have distance. And then the secondary parameters. So this is the data that we're going to use now. If I now project this so that you see, again, X and Y, but now for the data that you have spectroscopy, then you see, for example, that a lot of results. So this is the bar, no? I'm drawing here, and you see that most of the surveys, a lot are from the north, so they are not seeing the bulge in the inner disk, like Lamost. And in the south, what you have in the south, which is Gala and Rave, they do not reach the bulge. But now you see why the third revolution comes, and this is the reason. It's apogee. Because this magenta thing here is the apogee, and is the survey that is reaching the bulge and the galactic bar and the midplane of the galaxy. So that was a revolution because apogee was from a small telescope, it's an infrared spectrograph, was constructed in the north, but then had a brother in the south. And when they made in the south, we suddenly had the two hemispheres again. So this was part of Sloan, right? So Sloan 4. So apogee north is here in blue, and apogee south is here. The two is in red. So you don't do only the galaxy disk, but you did also other things. In the north, you did the Kepler and so on, Kepler. And so this is what has happened. So what has happened? Before I show you these two plots, which is Gaia plus photometry, and I said there was a hole here, right? In this box here that we call inner galaxy, there is 30 million objects in these maps. Good. But then I combine with what I have for apogee here, and in this box, with spectroscopy, I have 30,000 in the box. So 30,000 stars that for the first time are reaching the inner galaxy with information, parallax, information, 6D phase space information essentially, right? And chemistry, because apogee is a resolution 20,000 in the infrared. So you have chemistry for several elements, and you have chemistry for difficult elements, such like difficult elements in the sense that you do not usually have in the optical. Carbon, nitrogen, for example, they are very useful to trace timescales, for example. So this is then the third breakthrough, because if I look now the galaxy edge on, the mapping is already making that we can leave the galaxy and say, if I see the Milky Way edge on, that's what you're seeing. These are most of the surveys. No? Around the sun you have several. Usually they are in cone form because they are avoiding the disk with high extinction. But apogee is extending a lot to the outer disk, to the inner disk, and very close to the midplane. So finally, we are having a way to map the galaxy where most of the stars are. And this is, of course, a breakthrough for who wants to do galactic archaeology. A lot came out from there, okay? Especially into this square here, where you didn't have data before at this level. So if I look to the same galaxy in X and Y, you see again the apogee here. But why did I put the same figure I showed you before, but from the other paper? And what we are doing later in another thing, what we are doing with Foremost is that you see that we are lacking data here. All the southern hemisphere we have lack of data. And so Foremost will cover that part. We will cover this part. But there you have already a lot also from Lamost. Okay, so the main points up to here are that we are now able to obtain this chronochemical kinematical maps. We have the data for that over much larger volumes than before, than what I showed in the beginning of the first lecture. For this, we have the 6D information, and this volume will still extend a lot with Gaia DR4 and then the big spectroscopic surveys you're going to have. So this is all to change. We have then finally this large multidimensional information from chemistry complementing Gaia. And we have still the one more key dimension we discussed last time, most of it coming from seismology, but from isochron ages for nearby stars. You also have in this last paper with 11 million objects for which we had spectroscopy and Gaia, 2.5 million had ages. Ages from subgiants in Sikoternov, from the different spectroscopic surveys. So very important now, which was the question that I had in the last lecture, is to combine this information where you go with a very high quality data to the sharpest view of some problems, and then you can check if this is true with less quality data. And you have to get more or less same answer and understand this in a more holistic view of the Milky Way. You have the data for that. So the next steps now in how to use this information to check, to understand about the formation of the galaxy, and some of the things that you understand about the Milky Way matters for how you see the formation of other galaxies. Even if we are just one galaxy, of a certain type with a certain bar. But we have a bar, we have a merger, we have everything it takes to give some insights to other galaxies and galaxy formation simulations in general from cosmology. So the first thing that happens is that we see that our Milky Way has a thin disk and a thick disk. Of course, we knew that, but now we can map this thin and thick disk. This is very important for the Milky Way, as you're going to understand right now. So we had a view about the thin and the thick disk very local. And this thin and thin disk was showing a characteristic. And now we can see if this characteristic go further away or how is that. And we can use the information to understand this thick disk. The answer to that is that the thick disk of the Milky Way seems to have a shorter time scale. But now when I'm in the Milky Way and I say thick disk, I have to use another word and say the chemical thick disk. And the chemical thick disk will be the high alpha population. Remember we discussed the alpha over iron versus iron population as a curve, but reality is that there is not a curve. There is two blobs. There is the thick disk and the thin disk. And so there's been a lot of things to work out this. And so what I'm going to call the genuine thick disk, the thick disk that's formed early on, is the chemical one, the high alpha one, okay? But if I would look at the galaxy from outside, I would see a thick disk that's a combination of different stellar populations. And that's the key point that we see for our galaxy. That's very hard to see in another galaxy. So what has happened? So this is the key plot. What has happened when we have combined apogee, Gaia photometry, our spectroscopic, our star horse? So here you have the famous alpha over iron versus iron plot that I showed you before. And now here you have, down here, you have stars that are below, now here, 0 to half a kiloparsec from the midplane. Half a kiloparsec. Very close to the midplane. Now here you have from 0.5 to 1 kiloparsec from the midplane, and here you have from 1 to 2 kiloparsec from the midplane. Now, when I walk from here to here are beams between galactocentric distance 0 to 2 kiloparsec, so very central, and then I go beams of 2 kiloparsec. So I go from the galactic center 0 up to 12 kiloparsecs here, okay? First of all, you are seeing that if you go to the solar vicinity, where we had a lot of data in the beginning, we were sitting in a situation at 6 to 8 kiloparsecs, and a lot of data were not very close to the midplane. They were more like here, and we have that the alpha over iron versus iron is not just that simple curve I showed yesterday, but it has two blobs, and seems to have a discontinuity in between the two. This is what the map shows. So the map is showing you here, first that you think you see is that you have two blobs, you have always these two blobs, and you have these two blobs here in the inner parts very clear. Inner parts very close to the midplane, was not seen before, okay? So what is this? And you also see, and this you knew from very small data sets already, that as you go for the outer part, the upper alpha group here seems to disappear, even though I am above the plane. The thick disk is disappearing. This is why I'm saying the chemical thick disk has a shorter scale length, because the high alpha stop. Let me just move here. That is continuing the same plot, but now I'm going from 10 here, 12, the last being we were seeing the other plot, and I'm continuing to 20 kiloparsecs. This is also amazing, because Apogee has the Apogee Norden. We managed to do a very nice survey of the outer disk of the galaxy. What is amazing is that it's homogeneous. It's the same data set. So this is the first time we can see this in this way. So now here the upper blob disappear completely. You have only the low alphas. And what's more interesting, at all heights, you have the low alphas. So what this is telling you, the low alpha should be the thin disk, the one where you had time, the type 1a to contribute, thin disk forming a longer time scale. This is what I'm going to show now. But why are this low alpha up there, right? So, and here above we plot the kind of precisions that we get from the Gaia data plus Star Horse plus the extra information. This is the precision in distance, around 10%, and in the extinction, sometimes you have two blobs because in some directions you lack some photometry. But we did this because I was very worried, are we getting good distance for the innermost parts of the galaxy? We have something with uncertainties of the order, with a precision of the order of 10%. Precision, but we don't have accuracy, which means that you could have shifts on this distance. But that's why this plot is nice, because you are interpreting it relatively, not absolute sense. But okay. So one of the ideas is that the disk is essentially this. The thick disk of the galaxy, if we look from outside, is made from, the original one is really like this very old thick disk, high alpha, but then the younger populations are flaring when you go outside, bending, and so you are seeing the thin disk essentially high up, you see? So that's why if you would measure a thick disk, you would see a gradient in age. A thick disk geometric, but not a thick disk genuine. So this is the genuine one, this is the geometric one. Okay, so this we discussed last time. I'm always talk about alpha Variron, but alpha Variron is one clock that we have discussed last time. We have discussed this plot here, no? And if you are interested, I have this Sky and Telescope article here where I try to explain all this with some easy ways to understand the knee and everything we discussed last time. This is a very nice image that I wanted to just put here. This is a supernova type 2 remnant, where it seems the pulsar was kicked out. And this is just to tell you that in the reality these things are happening. This is chemically enriching our galaxy. And in the end, you have the periodic table. So in the beginning of the universe, you were here. Your periodic table was very easy, just 3 elements. And later on, you build up the chemical elements, as we discussed last time. And here, by either low-mass stars, exploding massive stars, exploding white dwarfs, which are the type 1a that we discussed that make a lot of iron, and merging neutron stars, each one on its time scale. And that's what abundance ratios give us the idea of time scale. And we discussed alpha Variron, but I can use different abundance ratios. Because if I pick up 2 elements that are made by different nucleosynthetic sites on different time scale, I can also learn about time scale. And this is the difference of the time scales that show me, the Milky Way has a chemical thick disk, has a thin disk, has something between that has a break. What does it mean? I interpret this as a quenching of the thick disk. The genuine thick disk formed very early on and was quenched, but there is a lot of discussion on this. It's not a final. There's a lot of debates. But I can take other 2 elements. So here I'm using clusters. And here you have, for example, yttrium over aluminium or yttrium over magnesium from different families of chemical evolution versus age, because I have cluster age. And if you plot this, you see this dependence on abundance ratios with age. It's not only alpha Variron, okay? The problem is that to have a lot of these elements, you need resolution. You need the high quality spectroscopy, and it's not always available. That's why you need to see what we're going to choose. But if you found something that has different time scale in an element, it should show up also in another element. And you can check now for a smaller sample because you have the data. So this was a detour that I made and that I just want to get back now to this part here. So essentially what do we talk about the thick disk, and then we saw that the thin disk was this low alpha part, right? The thin disk is essentially lower alpha. Why? Because it formed a longer time scale, inside out, and you had time the type 1a to contribute to this. So it was that part of the curve that was going down. So you had the plateau, I mean, the schematic view. You saw reality from apogee is different, but a plateau, and then a knee, and then down as when you have more iron coming. Okay, so the way we model this in chemical evolution is that for different radius of the Milky Way, so at these different radial beams that you saw, I have different star formation history. So it was more intense in the inner galaxy and less intense in the outer galaxy. How do I know that? Because we have in our galaxy the abundance gradients. And we believe that to explain the abundance gradients in our galaxy, you can, and in other galaxies as well, you have an inside, this is what we call inside-out formation. Very efficient star formation in the inner parts and very inefficient star formation in the outer parts. Okay? And this is the build-up inside out. So the effect of this, so the number of stars formed per parsec square per gigayear as a function of time in a chemical evolution model where there is no mixing, it's just the gas, doing the evolution of the gas after all these stars of different mass and age die, translating to an abundance gradient if I do only for the thin disk. So iron versus radius, and then I have very old stars here, and then I go up. I enrich the interstellar medium as a function of time, but I enrich it more in the inner parts and less in the outer parts because the star formation is stronger in the inner parts, and this is the build-up, the gradient. The thing can be completely different, and it's not going to start from a very steep gradient that then kind of flattens to the value today. It can start flat and then steepen depending on your initial conditions. So this is a toy model. We all fit the final, which is what we see today, but the problem is as a function of time. Okay? So if this was the full story, it was great, because now I have good data, I have good chemistry, I have positions, and so I can do the gradients. I have ages, so I can turn down the gradient backward, and I can see who are contributing more to the chemistry at which time scale. So I'm giving strong constraints to inside-out formation of our galaxy, star formation history, but also nucleosynthesis, if I go for different ends. But remember, I always will have the but in this lecture. As we said in the first lecture, there is this problem. This is radial migration. And this is a plot like the one we discussed yesterday. You have to understand the Alpha-Variron plot, otherwise I would not finish the lecture. This is the plot I want you to understand. So if I go to the solar vicinity here, and I take all the stars that are between 7 and 9 kiloparsecs from the galactic center, and are below a height of 3 kiloparsecs, right? So this is a model, it's not data. Now it's a different model. It's not a chemical evolution model. It's a simulation painted with chemical evolution. Okay. So if I take the stars that are here today, and this is what this green, this little square here is showing. This is number of stars as the burst rate of the stars. But I don't know the burst rate of stars. I know the stars that are here today. So if I take all the stars here today of different ages, and this is what I observe actually. I observe a number of stars, a function of metallicity around us. I can see from the model that a lot of them are not born here. Not born here. This is burst radial. There are stars today here that were born in all radial of the galaxy, according to the simulations. So for each volume I look, there are stars born here, but stars that were born inner and stars that are born out. This is radial migration. And when the star migrates, it brings its chemistry. Chemistry is not going to change with migration, but its kinematic is affected. Angular momentum is not conserved into this, and the star can be here in a orbit around the in a low eccentricity orbit, because it was kicked here. So it looks like a thin disk, but it's not. Or it is the thin disk from another region, and I cannot tell. The only thing that made me tell this is to put together chemistry and age, okay? And we see the tips of the iceberg. So this is a prediction of anybody's simulation that is mixing a lot of stars from here and there. The problem is the source of this mixing, okay? So one thing that's important here is that, look here, the stars that in this simulation were born between 7 and 9, which should be all of them if I didn't have radial migration. They are this green one here only. But you have an excess of stars of more metal rich than the current metallicity of the interstellar medium here that cannot have born here in this simple approach. Because the simple approach is you increase the metallicity with the time and you reach the value we see in the interstellar medium here. This is which is solar, more or less. A little bit solar, 0.2 solar in iron. Here, only radial migration. And then you see that you have an excess of stars. We know we have super metal-rich stars, as we call. You have an excess of stars that are more metal-rich than the sun. And in the model, these stars here are coming from 3 to 5 kiloparsec. They are not born here. So these are the migrators, okay? Okay, but you say, okay, but this is just a model. Who believes the simulation or whatever stuff? So that's exactly the point. We want to see, is this true? So this is the tip of the iceberg here. You see, wow, these are the clearly migration. The others is difficult to tell, right? Because it's very difficult. So we find in the solar system old stars. We find a broad range of metallicity. We find this tail. We find above 0.2 solar metallicity. We call them migrators. They cannot be formed here. Okay. Now we can do the model for different galactocentric. I show you the beam around the sun of what we had in this model. And if I move to other beams, there will be different amounts of mix between stars. And ideally, I want a map that can tell me how much I'm migrating, who is migrating. I want to know everything so that I can know the impact of this in the galaxy and if we can still extract the inside-out star formation history. Okay? So if I do the age-metallist relation, which is iron versus age, the famous age-metallist relation, in a chemical evolution model, it's just a curve. And in the observations, you see there's a big scatter. Why? Because it's mixing the age-metallist relation of the different radius. Because I just told you that the stars at each radial beam that we were looking before in the data, they are a mix of stars from different beams. So this is exactly what we see in the model. This is the model. So you predict that this is scattering the age-metallist relation. Will have a different shape. And then with that, different age distributions, you could put constraints into this problem, into this thing. How are you going to do that? Well, you need ages. So we discussed last time difficult. Around us, we can use Kepler, TESS. Now, I didn't talk about TESS, but TESS is also seismology, K2, Gaia, and Gala. And when you go far away, you are left over with the seismology aids of these beams that were going far away. So it's not going to be an easy job unless we have a full, completely map of the Milky Way with ages. It's not going to happen right now, but it's going to happen later. Okay, forget about plot. So the first thing we did, we combined then apogee with Kepler, gave the input to the Kepler data from spectroscopy. Remember, we discussed that the astroseismologists give me mass and radius. But how good they are depends of some information I have on temperature. And so I get, I use this on these data sets. This data set is Kepler field. We saw yesterday, it is in a direction that most of the stars are around us, 7 to 9 more or less. And for those stars, I could date the stars. And so by having apogee, Kepler, and Gaia together, in this paper, it was possible to age the stars and plot that plot we were just looking before, but with data. And what you see is that the most metal-rich stars in this plot are essentially older. They are not the youngest. So this is the tip of the iceberg, is really right migration. Okay. So where did they came from? This is the last lecture. So another thing we could use for is to trace the abundance gradients. I said that we have the abundance gradients today, and this is giving me a constraint in the star formation history, right? And so we can use now the information we have from seismology, Gaia, plus spectroscopy, and we can do this. So this is a gradient, iron versus galactocentric distance, right? And these are data that usually we manage to trace the gradient today in the galaxy by using H2 regions, Cepheids. Why? Younger objects that trace the values of the abundance today in interstellar medium. That's what an H2 region is, a Cepheid, which is a massive star. That's what they are tracing today. So I have the abundances traced by Cepheids, open clusters, young open clusters. They trace the gradients, right? And then here on the top in blue, you see the coral stars, coral apogee. So seismology plus spectroscopy, ages we got. And then we say, okay, if our ages are not bad, but they are giants, we get seismology for giants. Remember, I told you precise ages are for giants because the mass-age relation is simpler than if you go to another part of the HR diagram. So these are the blue points. These points are stars that are younger than 1 gigayear, around 1 gigayear. And the coral stars are on the top. The coral stars for which I got younger ages are on the top of the abundance gradient today. Okay, so we are doing good here, because if they were not, there was something wrong. And now I can walk in time, because now I have age for field stars. That's the difficult. Age for field stars that are far away, so they can trace the gradient as a function of age. Otherwise, I cannot do that. So I go now. So you have predictions. I'm showing you some here of another group where again you have what you predicted, that the gradient was steep and then reached the time today for a specific chemical evolution model of the Milky Way. So other groups here. And what we predict from this chemodynamic model, just show you the the prediction, the solid curves here of the gradient is the same model I was showing you before, and with the dotted is after radial migration took place. So if I put an initial chemical evolution model and let the particles mix, it destroys my gradients as a function of age, of course, right? For the very young, you still get the gradient, but if I wait too much, things mix too much and I lose my gradient. So that is one explanation for why the gradient of the older times could be flatter. But another explanation is that the gradients were flatter in the past because there was some pre-enrichment. So that is this difficulty, okay? So this is kind of prediction of chemodynamic models. But what the data shows now, and this is in other galaxies, also some flatter gradients obtaining with different ways to get distance, also get some flatter gradients in the past. This is the gradient versus time, flatter gradients in the past, reaching the values of minus 0.06 more or less, which is seen in galaxies. Okay, so let me just go here. Now I have Corot, I have ages, I can go far different distance. So now again here, the gradient we were just looking at big plot, but now I'm plotting only those that 1 to 2 gigayears old, 2 to 4 gigayears old, until I get very old stars. The gradient is destroyed. There is a scatter. Here to trace your eye, this is a chemical evolution model curve of those curves that I show you. And this is how the radial migration is scattering stars around that chemical evolution curve. So the mixing of stars among the different radius, the points from the simulation we had. And you see that in the very first being, 1 gigayear, the points are almost above on the curve. Radial migration didn't have time to move stars too much here and there. But as long as you got here already, you have a lot of stars moving out from the chemical evolution curve to the point that you get here and you have a very flat. If I construct a mock catalog using the same selection way to select the data, this is what you have in the mix. I take the simulation and I select the same way the Corot fields are placed, and that's what I get from the model. It's quite similar, okay? So we got with this way the evolution of the gradients with time, but that does not mean that it's the original evolution. You see? Let me jump this just a second. Wait, here. This is more clear. Now, once we did this with Corot, but then we say, okay, if that's true, what about the open clusters? Because the open clusters can be traced very far away, and I have the ages in the disk. So, for example, in this paper from the clusters from Apogee, I put the clusters with different ages over our models, and the clusters are above the curve here, you see? They are more or less where the data are. So essentially the clusters are radial migrating as well. Not only the stars, the clusters also radial migrate. And this particular Apogee had a very good coverage of the disk. I can go and do this with K2. You saw that I had different directions of K2. I can do the same thing. The K2 data is from seismology aids. I got is the green thing here. Overplot are the same clusters that we just saw in the transparency before. And you see that the K2 is telling me field stars old that tend to be above the expected gradient from a pure idea that things are not moving around. So you're seeing radial migration happening here in this data. This is too complicated now. And finally, this plot I like to show is another survey of Ocaso survey, another global open cluster surveys with very high resolution in the NOTE telescope. And here you see, here up is clusters that are younger than 1 gigayear, clusters that are between 1 and 3, and clusters that are older than 4 gigayears. And what is here is interesting is that if you look to 8 kiloparsec here, which is solar vicinity, what do you see? You see that older clusters are more metal rich than younger clusters. Understand this. Metallicity should increase with time in a simple chemical enrichment approach. So older clusters should be more metal poor than or young clusters at the same position if they were born here. But you are observing that the younger cluster at the same radial beam, older clusters are more metal-rich than younger clusters. So that's also tip of the iceberg, and as you can get also another explanation, but is matching together with the fact that there is no simulation where the stars stay where they were born. Okay, so radial migration seems to be a big thing. Okay, so here I have some minutes, I guess. Who is controlling the time? Okay, Martin minutes, perfect. So you saw the importance to have ages, good chemistry, going far away. And this was even before Gaia, because I had the seismology or I have clusters. Yeah, because before Gaia, if you have a good distance, you need either seismology or clusters. I mean, you could not go another way. Now you're going to be able to do for thing. And now you say, okay, but we saw this alpha over iron double sequence and so on. Why is this happening, right? And so I told you about the chemical thick disk. So we have to, the way to answer this is like this. Was the thick disk formed very quickly and then the thin disk formed in a longer time scale? And this time scale is varying from inside out, okay? On the top of that, you have radial migration, so it's not simple. But can we have that plot painted with ages? We have some in the literature, but they are very, very uncertain ages. But we can have very good ages at the solar vicinity. We can have good ages. So we can see, is this high alpha population really old? Can you really date that thing to high precision? So this is possible. So essentially, if you plot an alpha over iron versus iron, look at the plot here, in a 25 parsec sample, you see this plateau and you see this discontinuity. This is the famous Fuhrman plot using Hipparcos data. That's why I started the talk with Hipparcos. So this is in a 25 parsec. We talk before 20 kiloparsec, okay? But in 25 parsec, this is a volume completed sample, and he has very good information. He has very good isochron ages. These are subgiants. And there he could see that the high alpha plateau is very old, and you have a different age as you go to the thin disk. Okay, was the started. This is 2010, but I had the first data already in 98. Okay, so that was the interpretation that could be that during my PhD, I gave this interpretation. Actually, what you are seeing is that you have in the plateau, here is upside down. That's what I put here. So this is how I show you the alpha over iron versus iron. And his is the same, but it's upside down. Iron over magnesium versus magnesium. And the reason is that magnesium is coming from type 2 supernova, so it goes more linear with time. And you see this gap more clearly, but essentially the same plot. So how I interpret this? I interpret that you are there forming something very fast, a thick disk or in a disk, and at some point you will form the thin disk in a slowly process. But something happened that you had a jump, because you have a gap in this data. It's not continuous like the curve I show you. There is a gap. So the interpretation was that this jump can be translated into this, a first very fast formation episode for our galaxy, a quenching meaning stop, something has stopped the star formation there, had to wait, more gas was brought up, you got a second episode of star formation, okay? This was what was called the two-info model, but there are a lot of other interpretations, but people have been concentrated a lot in explaining why it was quenching. Is the quenching the one that's explaining this? Or is the radial migration that's provoking this thing? And you are thinking you can interpret as a quenching, but actually there is no quenching. Okay, so the key answer is the age. Okay, more data from this very beautiful paper by Eric Nissing with amazing data where he controlled very well all the data. He also sees two groups here using another indicator of yttrium over magnesium as a clock, another kind of clock. Also sees something that seems to have a 2 period. So, but now we have Kepler. We have Kepler, apogee, and we can get very good ages. And I can do the alpha over iron versus iron plot I showed before, finally in 2021, I had to wait a bit, painted by ages. Age is good to the 20% level. And what are you seeing? You're seeing the low alphas are younger, but there is a degradé going a bit older. So you were a bit higher alpha, and the age is varying here, but they are very old here. The high alphas are old. you have these red dots here. They are so-called young alpha rich because, as I told you, the ages from seismometer come from the mass, and when you have an accretion of mass, this mass is not anymore the original mass of the star. So the star looks young, but actually it's not young. I mean, it looks a bit more massive, so younger, but it's not. It just got mass over it. And that's why you have these outliers here. This is the same data, but I'm plotting age versus alpha over iron. I can do that. And so forget about these young alpha rich. I'm not going to discuss them here, but look to the older stars. At the moment the alpha over iron has crossed 0.1 dex, there is no scatter anymore, is a coeval population showing up. Coeval. These people here are old. Old within 1 gigayear, okay? And at younger ages, you have at lower alphas, you have a mix of population. This is very important because if we now plot, this is the posterior probability distribution function of the age spread of that population, I can, with 95 confidence level, tell you that the scatter of that coeval population was below 1.2 gigayear. So the high alpha population at here, so you saw that high alpha map, high alpha, low alpha going from center to the outer disk. But the piece that passes here, for which I have good ages, I can tell you that high alpha was formed within 1 gigayear. The thick disk is very old. I'm talking about an age of 11 gigayears. That means at redshift above 2, this thick disk is in place. Okay, that's what it means. So this is a very important information. Okay, but now there is a gap. Is there a gap? Remember, the idea is to translate the alpha over iron high and low into 2 episodes of star formation at the solar vicinity. But there is a different as you go. So what we take? We take the age and the number of stars. And you have, and we simulate these fields using trilegal simulations. And essentially, we see that we have a bunch of old stars, then a distribution of age, and it seems to be a discontinuity. But the age uncertainties are still a bit too high, 25%. And I cannot say for sure that there was a discontinuity here in age, okay? So, but you can say, okay, but if there was a discontinuity, this two population should have a different chemistry, kinematic, could have a discontinuity in kinematics as well. There I can also do, because now I have also the velocities, radial velocity, I can measure the velocities very well, so I can plot the velocity in the z direction, so not in the R, but in the z direction, as a function of age. And I can also plot the velocity dispersion. That's very important of a population. So if the velocity dispersion is very high, this thing is rotating less. The thick disk rotates less than the thin disk, but we know that. But if there was a continuity formation from the thick disk down to the thin disk, you would expect a continuous decrease of the velocity dispersion. But we don't see that. We see that the thick disk has velocity dispersion of the order of 40 kilometers per second, and then you have an increased velocity dispersion as a function of age in the thin disk, but you have a jump. Okay, so it seems to have a discontinuity also in kinematics, in age, in chemistry. So this is pointing to us that the thin disk and the thick disk of the galaxy are two different stellar populations, and not just the continuation from one into another. And this is giving you an idea, an important idea about how our galaxy forms. So that means if you go to a redshift of 2, you should be seeing how would our galaxy look at redshift of 2 when, like, say, 10 gigayears ago. How would our galaxy look? You would see a thick disk. And when you go to the recent data in redshift 2, you see thick disks at redshift 2 that you now can measure. And what is the velocity dispersion of this thick disk? Is around 45, 50 kilometers per second. So it's very nice, okay? So I'm finally asking you, do we see a bimodality? I showed the bimodality in age for you for this sample for which we had good age, but do we see then, as you go up to the middle plane, do we see this bimodality in age going up? We can use then, now, we can use K2. So K2, for example, here was the Kepler data I'm showing you. So almost all the data is at galactocenter distance here. Here is the height above and below the midplane. But with Kepler, I have these two fields here, where I have seismology. And I can compare the age variation as a function of the height of this population. And that's what I have. For the Kepler K2, for the K2 sample where I had spectroscopy follow-up, I can see that the high alpha population is old, this red line. The low alpha population tends to be younger, and there is a discontinuity kind of situation. For the data, for the K2 sample that I didn't have spectroscopy, I can do it in a different way. I can look to the stars that are very close to the midplane. They will be dominated by low alphas. And then I can look to the stars that are very high above the plane, which they will dominate at the solar vicinity by high alphas. So I see also this very close to the plane is the green, more young stars. Very far from the plane is the older stars. Again, the blue is the sum of the two. So you have this distribution. The problem is with the K2 data, you reach 30% precision in age. Okay, so this I show you already, sorry. Okay, so I will finish now this lecture by saying this is the plot we did by using Gaia, Apogee, and photometry. And now we know that here at the position 8, or in these beings here, in this being here, we know from another data set where we had K2 that the people that are here are formed within 1 gigayear. They are very old. And now you can ask, okay, but is the characteristic of this high alpha population changing as a function of radius? And there's a lot of papers showing it doesn't. It doesn't. The thick disk here is exactly like the thick, we call the chemical thick disk this. The thick disk here is like exactly the one that's here, exactly the one that's here, and is the one that's here. Because it's a coeval thick disk that form very fast. There is no gradient. There is same alpha over iron values. You see, so it's a coeval population forming, but at some point you don't see it anymore. Remember, when we go beyond, the high alpha disappear. Because this old thick disk was not a very, didn't go beyond 10 kiloparsecs from the galactic center. It was shorter scale length than the thin disk. So this is very important, and there's a lot of cosmological simulations trying to see this in other galaxies as well. What is making this thin disk, okay? So, the last two lectures we're going to focus here. This is what I'm going to call bulge. Because this whole part here just appeared after we had this data. After data release 17 or 16 of Apogee, plus the Gaia that brought us to this region with good distance, plus the fact that now for a subsample of those, I can do orbital analysis, which I haven't shown you yet. So there I can have a completely different new way to look to the bulge, because the bulge usually the studies are radial velocities, you look in L and B, you find the populations, but here you're gonna see that you have a mix of populations in the bulge. You have an inner thin disk, you have an inner thick disk, you have maybe an old spheroidal bulge there inside, and more important also, you have a reservoir of very metal-rich stars. It's from there that the stars migrate, and those super metal-rich we discussed here in the solar vicinity, they are coming from there. So there's a lot thing happening there, but we are still seeing very little. And as I showed you before, we had a box around 20,000 stars from Apogee. That's the last release of Apogee in that region. And the stars for which I will have good orbits and we'll go through this analysis with you is reduced to 8,000 stars. So that's, again, answer your question, that's the limitation. Because 8,000 stars to disentangle different star population in such a crowded and complex region is certainly not enough, right? And for many of them, we lose, because the 8,000 stars, why? Because as I told you, Gaia cannot peer the dust. So you need more data there, you need Gaia and infrared, that's what you need. So we are limited. But if I tell you we have we have now 10 different spectroscopic surveys covering all the galaxies, it's not true. Because when you are in the inner galaxy, and it matters. Why it matters now? Because now you know that a lot of the stars in the inner galaxy are coming here, in the solar vicinity. So you have to understand the inner galaxy, the bar, how the bar is kicking stars here, how other mergers with our galaxy have kick stars here, to then be able to do that reconstruction of the galaxy that we wanted to do and talk about in the next lecture. Okay, so I stop here. Thank you a lot for your attention.
So thank you, Cristina, for this really amazing lecture. So questions?
So you just said a sentence in the end that was my question here since the beginning of your lecture. So what's the role of the bar? And to what extent this role can work on the disk?
Yeah, so this is really where a lot of efforts are going. So how can people answer your question? First, trying to study the properties of the supermetal-rich stars here, going to more detailed chemistry. So that's a way to understand those supermetal-rich stars, their distribution age, their distribution in chemistry, and you see where they're coming. The second is to study the stars there, and trying to understand this different star population. And so, from the point of view of data, that's where we are, and there's a lot of paper being made right now. From the point of view of simulations, there's a huge problem, because if you do a simulation which is called a non-cosmological simulation, you can have a lot of details, and you can put a bar, and you see how you form a bar now with buckling and so on. But then you have some simulations without a very good modeling for the gas, and the gas matters here, because the bar is going to form, that there will be gas flows and so on. So this is one problem. So this will make it's difficult to quantify the migration from first principles, because different models will give you different answers. But then there is the problem, which I haven't touched at all, that we have been kicked by stuff, and we are still being. We interact with the Magellanic Clouds, we have the Sagittarius that kick us, and in each of these events, you can promote more radial migration. So the things are not linear. So to model that, you need a Milky Way-like galaxy formed in a cosmological scenario. You need the cosmology simulations, because they are going to have the merger rates. You have to find a Milky Way-like galaxy in a cosmological simulation that can do good star formation, that has a resolution, and has a bar. Now, how many of those we have nowadays? So the first problem is that cosmological simulations have problem to form bars. First problem. So this is already problematic. So the way to do now, I think, is to work on a little bit on different things. Like some people are trying to model some of this data of the bar, and here this data is amazing. You have also the velocity distribution of the bar. I'm going to the third lecture, we see this. So this is ongoing. What you want to know is what we wanted to know. I mean, there was an impact that's clear, there's going to be, but we don't know how to model it very quickly now.
Another question? Questions from the students? Don't be shy.
Pode ser em português, gente.
Yeah.
Não ficou claro uma coisa? Cris, não entendi nada daquele plot. Pode falar. This is student, I know.
Are you able to map stellar streams with Star Horse? Have you found some of them, or are you tracing some of them?
You can. We have, so that part of the streams, and I'm going to mix a little bit with the bulge, because some of the Christian stuff could have stayed in the bulge, so it's bulge halo, so it's not here in the lecture yet, but it's going to come. So you see, for example, it's very nice. You can, for example, trace also the Sagittarius stream. We got more information about using this for like the leading arm, the trailing arm. We get the different ages. We get different ages for the trailing arm, leading arm, and these other things is possible to get. So, but there's a lot of people concentrate only in the halo and the streams and so on. But yes, this data is giving you a revolution in that area as well.
Okay, another question?
Hi, Cristina. I'm going to ask you in Portuguese. Is that okay?
Yeah, of course.
Okay. Você mostrou um plot fala sobre eficiência de formação. É só uma pequena deformação de estrela.
Mm-hmm.
é mais eficiente próximo ao centro?
Sim, sim. Uhum.
Só por curiosidade, não é simplesmente uma questão de material de formação? Você tem mais material para formação?
Você tem mais stellar density, desculpa, você tem mais densidade estelar nas regiões internas, tem mais material.
Okay, Cristina, sorry, there is someone that I think does not understand Portuguese.
Okay, sorry. So exactly. So
okay, the question is about the plot where you show the star
I know.
efficiency. The question is, why are you calling efficiency? Because if there is more mass towards the center of the galaxy, so it's just a matter of, because there is more mass, it's not a question.
Yeah,
of
that
efficiency.
is important, and I haven't talked about this. If you do only because of that, you cannot reproduce the abundance gradients. You need an extra factor in front of. It's not just a question of how much gas was available.
Okay.
So it's not a question of only a simple Schmidt law that is making that as a function of radius. So the time scale of accretion of this gas into the Milky Way is varying as a function of radius. So here the accretion takes some e-folding time longer, like ET minus over tau, like 7 gigayears, and in the inner parts I run a chemical evolution with like 1 gigayear. But if you do only this, you're still not going to have the gradient thing. You're going to need a factor in front, and then you can use a factor, and I'm calling this efficiency.
Okay.
But you're right, it's not that correct. Yeah.
Another question?
Cristina, I know that all these results are for our galaxy, but what about Andromeda Galaxy? Do we see something similar to what your results about this mixing of the stars? And
Yeah. So first of all, let me give you an opinion very clear that I have about these two, high alpha and low alpha. I don't think radio migration can explain you that. Radio migration is mixing the things in the low alpha, but it's not going to make you a high alpha, low alpha, okay? Then it's very important to know what's happening in another galaxy. There's recent people trying to do that. The difficulty now is that you cannot have the same vision I have of individual stars yet, because you're not gonna get those. So people are trying to do, there's a very recent paper by the people from Apogee. They're stacking the Apogee. They have a lot of spectra from M31, and they are trying to analyze this in an integrated way. If you see the high alpha, low alpha, and apparently, if I'm not wrong, because I just saw this, you don't. So this is a key question. Is this high alpha, low alpha in all spiral galaxies? Is only ours? So now you can ask this same question to simulations. So what do the simulations? When you do a simulation of a spiral galaxy, do you have this? So now is a mess, because you have some simulators saying you do. And they were linked to the fact that the galaxies that had a very strong accretion moment, which I can understand. Our had. The Gaia Enceladus kicked us 10 gigayears ago and could have the reason to stop the star formation of the thick disk. And then at each accretion event, you bring a lot of gas. And then broad gas, and you start at the thin disk, then inside out. But not all simulations agree on this fact too. So some simulations say that only 5% of the galaxies had this double thing. Others say that all of them has. So it's very difficult, and this is, if you read the literature, it's a bit complicated. That's why I'm saying this is happening right now, this discussion, and there's a lot of debate, and because the simulations are different, and because they're very difficult to define a Milky Way-like galaxy in a simulation, because you need a lot of things to be a Milky Way-like galaxy. So there are simulations, for example, the CLUE simulation is a simulations in a local environment. There is a Milky Way and an M31 and some things that look like Magellanic clouds, because this matters too, right? And then you have the problem of the resolution of the simulations. The bars don't show up in a lot of the simulations. So this is a complex problem.
thank you.
Okay.
I'm actually a student. In the context of Ocaso survey, I think the plots from Casamichela, I couldn't get the role of radio migration in explaining the fact that older open clusters are more metal rich than the younger ones. So if you could go back on that,
Yeah.
please.
It's so hard to be older. I don't see anything anymore. Wait, here. Okay. Sorry if I jump here. I didn't even say that the different colors go for different nucleosynthetic sites. So alpha elements and capture elements that were in the... Okay. So you want that I explain this?
No, I wasn't able to see how radial migration explains the fact that we are seeing older open clusters with
Okay.
more
Okay.
being
Now I
more
understand.
metal rich than the younger ones.
Okay. So let me go here. Here. Let's go to another one here. So because let's suppose in the past you had such gradient, right? So you're forming star more fast in the inner parts and slower in the outer part. So the metallicity is increasing fast in the inner part and slower in the outer part. Let's suppose you didn't have any pre-enrichment in the galaxy. Because if you had a pre-enrichment, you started from something that was more or less flat. And then you're building up a lot in the inner parts, so you increase the gradient as a function of time, right? So here is a simple model of chemical evolution where you only have a thin disk, so you are very steep, because you had almost nothing, but inside you had something, because it's making fast. And then this is all increasing with time, because you're increasing in metallicity, and you are getting the gradient today. This is the line, okay? Now, I have a simulation, a cosmological simulation, a zoom-in simulation, for which we paint the particles. The simulation, we paint the particles with some chemistry of these models, because I know the chemistry as a function of time at each radius, okay? So I paint these particles with this, because I have the time, so I have the age of my thing. I painted it. Why did I paint the particles and didn't use the chemistry of the simulation? Because the chemistry of simulation was bad and there was no good star formation, because that's the problem of the cosmological simulation, difficulty. So I painted the simulation that was a Milky Way like ours. These are the points, okay? So now I'm in control of the chemistry. And the points are telling me that in the beginning, they are the younger points are sit on my chemical evolution model today. But the older stars, they migrate. And this is what you're seeing here. And you have a lot of more mass in the inner galaxy. You have more migrators come out from the inner galaxy, and some migrators come out from the outer galaxy. So what you see here, that an older cluster, you see these blue points, they go up from the curve. You see? Here, you have more blue points above the curve than below. And that means that if a globular cluster, it can think it as a test particle. If it was born in the inner region, it has a higher iron, and then it migrates here. But it had some time, it needed time to migrate here, so it can be older. But he's bringing his chemistry, because his chemistry is the fossil record. That's why it's galactic archaeology. He's bringing his chemistry, and his chemistry was formed in a region where metallicity was high. And then he's coming here, right? That's why an older globular cluster here can be more metal-rich than a globular cluster that was being forming here at that metallicity and was younger. So the younger one was sitting in the curve, was here. At 8, really, he was living and born here. But the older one was born here and was migrating towards here. I'm today looking the both of them here, and I'm seeing this. Okay?
So, Cristina, considering this migrating cluster, so how does the dilution time compares with the migration time?
What do you mean dilution?
Dilution of the cluster.
Well, so I don't know. The dilution time for the cluster depends where the cluster was. That's why we don't. The cluster, I never liked the cluster as traces of the gradient because of this, because the clusters in the inner galaxy, where are the older open clusters? They are not found in the inner galaxy. The oldest open cluster we have is in the outer galaxy, right? They were destroyed. And the only older clusters that survive are the ones that left the busy area. And this is why I'm seeing them here, you see? So a lot of the open clusters are young, otherwise they get destroyed. And they get more destroyed in the inner parts of the galaxy than in the outer parts of the galaxy. And that's why I'm seeing this in the end. So I don't know exactly how to compare the time scale, how they are being destroyed. This is a whole topic also being very much studied. Now with Gaia, you can have there's a complete area for open clusters. But it's amazing, because with Gaia you can clean the members of the clusters in a very beautiful way. You can discover new clusters, so you have a lot of this. So, for example, Friedrich is a postdoc now in Barcelona. He's specializing himself in working with open clusters, for example, because there's a lot to be doing there. Because for then you have the age, then in the open cluster you have this other problem, which is the diffusion of the stars in the clusters change the chemistry. That's a problem. I mean, changing the chemistry is a problem. For now, for this lecture, I'm talking only about the ones that have kept their chemistry intact. But if you destroy that chemistry and the kinema, then forget it. Then we forget about these objects. They are the imposters.
Okay, Cristina. So do the simulations can reproduce the disk flaring and also the warping?
The warping. I didn't put the warping here. The warp is beautiful now, traced with C-phase. Yes, the simulations always have warps and flarings, and this is also you see a merger pass by the whole thing. The disk goes like this. It's really like I don't think a warp is a problem for the simulations. Or I mean, to get the real good answer for the Milky Way, I don't know, but I think they can reproduce quite well.
So another question, last one. No? So let's thank Cristina again.
Thank you.